everyone, and welcome to yet another video of this channel. So today we are going to be solving a number theory problem from the PUMaC. The PUMaC is the Princeton University Mathematics Competition. So the problem reads, find the positive integer such that the product of its divisors is 8,000. And the reason why I like this problem is because there's really so much that we can learn from it. So usually the first basic intuitive approach that you might have if you aren't acquainted with any divisor relation formulas is to guess and check the first 100 integers and see one whose divisors do multiply to 8,000. But we don't really learn anything from that, and this isn't a timed test or anything like that. So what we're going to do here is we're going to derive a formula for the product of the divisors of a positive integer n. And then we're going to set that formula equal to 8,000 and solve. So let's see. So the first step is to find a formula for the product of divisors. So that's the first key step that we will have to do. So in order to find a formula for the product of its divisors, why not come up with some representation of the divisors themselves? So what we're going to do is we're going to let d sub 1, d sub 2, and all the way to d sub t of n, which I'll get to later what that means. And they're all n's divisors. Now, what does t of n mean? T of n is the number of divisors of n. This is the notation that we will be using throughout this video. So now what we're going to do is to find a formula, right, which is an equation in its own right? We have to set up equations maybe. And since we are looking for the product, maybe our equations should have some products in them. So what we're going to do is we are going to do n is equal to d sub 1 times d sub t of n. And I should actually mention that these divisors are in ascending order. So d sub 1 is the smallest and d sub t of n is the largest. So then we have this equation right there. And we multiply and we just have all the equations, which I think you can guess that we will start multiplying. And we have this last equation right here. Now, why did we write them all out? Well, notice. This right here, this column, if only that column were multiplied together, this would be the desired product we are looking for, also called P. So that's what we're going to call it because P stands for product. And then notice that this column also multiplies to P. They're just in different order, but multiplication is commutative, so that doesn't really matter. So that immediately gives us the idea to multiply all of these equations together. Now, what happens to the left-hand side? Well, it's n times itself a number of times, but what is that number? Well, there's t of n equations, right, as can be seen by these subscripts here, right? 1, 2, t of n minus 1, t of n equations. So if we multiply n together by itself, t of n times, we get n to the t of nth power. So what we get from this whole setup is that n to the t of n is equal to p squared, which immediately yields p is equal to n to the t of n over 2. And that is the formula for the product of the divisors, which we can't really set equal to 8,000 yet because we don't know what t of n is. So that's a really big problem, but we're going to solve it. No, we're not going to give up here. We're not going to resort to the guess and check method. And I'm pretty sure that you know what we're doing now. We are going to find a formula for t of n. So, let's see how to do that. And what do you think of when you first think of number theory? Well, if you know all the technical number theory, linear congruence and stuff, you usually think of that. But if you're just starting out in a number theory course, what you usually do is you think of prime factorization. And to some, it may seem really surprising that in all of this proofy setup, we still haven't used prime factorization. So that is exactly what we are going to do. We are going to prime factor n. So let's see how that works. we set up the prime factorization, and this right here, although this definition doesn't appear in many school textbooks, is really the definition of a prime factorization, right? All the p of 1s, all the p's, p1, p2, p3, pn minus 1, pn, those are all distinct primes. None of them can be equal to each other, but they're all primes. They can be even too, one of them can be 2. And all of these e's right there, they are all non-negative integers. So they can be 0 or positive, but they can't be negative. And this is really the definition of a prime factorization. So what we are going to do now is we're going to construct a divisor. So how does that work? Well, we're going to call that divisor D for divisor. And let's just call it P1 to the K1 times P2 to the K2 multiplied all through times Pn to the Kn. And why is this a divisor? Well, notice, can a divisor really have any other primes other than these n primes? No, because then it's not a divisor of n. This really is kind of the definition of a divisor. And just note that all the ki's, right, K2 for instance, it's less than or equal to E2, but it's bigger than or equal to 0. It can be 0 for instance, right? For instance, if we have 6, right, which is 2 to the power of 1 times 3 to the power of 1. In this case, P1 is 2, E1 is 1, P2 is 3, and E2 is 1. Then the divisors are 2 to the 0 times 3 to the 0, or 2 to the first times 3 to the 0, 3 to the first times 2 to the 0s, and 2 to the first times 3 to the 0s. So as you can see, all of the powers that appear in those divisors, they are all less than or equal to the original power that appeared in the actual number, but they're all bigger than or equal to 0. So if that was too wordy, you can kind of sketch it out in your own. Just try doing that. It always helps. So what we did is construct a divisor. So now our next question is, well, how many choices do we have for the divisors, right? Because that answers our original question. What is T of n? What is the number of divisors? And this is equivalent to saying, how can we choose all the k's of 1s? Okay, so let's answer that question. And what we're going to do is notice, we can find all the choices for each individual k and then multiply all those choices together. Because all of these k's, they don't have any effect on each other, so we can do that. So how many choices are there for K1? And actually, I just have to note, it may seem obvious, but all the Ki and all the Ei, they're all integers too. So how many choices for K1 are there, for instance? Well, let's see. By this right here, K1 has to be less than or equal to E1, but bigger than or equal to 0. Between E1 and 1, there are E1 integers. If we add 0 in, we add one more integer. So we get that there are E sub 1 plus 1 choices for K sub 1. And then we just do this whole drill on all of the K's, ending with the choices for K sub n, which is once again an integer between 0 and E sub n. And there are E sub n plus 1 such integers. And now what we do is we multiply all of these together. So, to get T of n, we multiply all these together, and this leads us to the grand formula, T of n is equal to all of these multiplied together. Now, that may seem like a lot of words, but what we're going to do is we're going to do an example. So, this is the example, and we are going to find the product and number of 120's divisors. Now, what we're going to do is we're going to find the number of divisors first, because we can't find the product unless we find the number. So what we're going to do is we're going to, just as in the proof for the formula for T of n, write out 120's prime factorization. It is 2 to the third times 3 to the first times 5 to the first. So T of 120 is this exponent plus 1 times this exponent plus 1 times this exponent plus 1, which equals 4 times 2 times 2, which is 16. So there are 16 divisors of 120, and you can list them out on your own if you want. There are indeed 16 divisors. So now the product of all of these divisors is 120 to the t of 1/20th, so 16, over 2, which is 120 to the 8th. And please don't ask me to calculate that. So what we did was we established all of the formulas that we need to solve the PUMaC problem. So let's just refresh our memory. We want to set this formula right here equal to 8,000. Great. And let's just call the integer that satisfies the original PUMaC condition n, because n is a really commonly used variable in number theory, and in general, it is really important. So we can just square both sides of our product relation, and then we prime factorize. So we have that n to the t of n is equal to 2 to the 12th times 5 to the 6th. Now what we want to do is we want to find out some more information about n. So we are going to do a proof by contradiction about one claim that we will set up. N is equal to 2 to the x times 5 to the y, where x and y are non-negative integers. In other words, the only primes that n has in this prime factorization are 2 and 5, no other primes. So what we're going to do is we're going to prove this by contradiction. I'll explain to you what that means later. So, BWalk by way of contradiction. Suppose that there is another prime in n's prime factorization, and let's call that prime p. So the aim of this proof is to say, so if our claim is false, right, that we just assumed here, we want to find something false with the falseness of our claim, proving our original claim true. So basically, we have that n is equal to 2 to the x times 5 to the y times p to the z, where p is not equal to 2 or 5, but it is a prime. So we have that n to the t of n is equal to, by basic exponent rules, the following expression. And we know that this obviously has a factor of p, right? Because it's right there. P is written here. But we know that this, from this right here, is equal to 2 to the 12th times 5 to the 6th. And notice that here, there is no factor of p, because neither 2 nor 5 is equal to p, and those are the only things in this right here. So there's no factor of p in this product here. But can something with a factor of p be equal to something without a factor of p? Of course not. The only time that can happen is if p is 0, 1, maybe -1, but none of those are primes, obviously. So this is a contradiction. We just arrived at our contradiction. We arrived at something false, which we call the contradiction, with the falseness of our claim. We just proved that our claim is not true, which means that it is true. Anyway, so let's just recap what we did. From the above claim, we know that n is equal to 2 to the x times 5 to the y, which means that t of n is x plus 1 times y plus 1. This means that n to the t of n is equal to 2 to the x times x plus 1 times y plus 1 times 5 to the power of y times x plus 1 times y plus 1. And this is equal to 2 to the 12th times 5 to the 6th. Now notice, we can match exponents, because the only part that will contribute to this right here is this, and vice versa. So these two parts must be equal, because 2 is obviously not the same as 5, and like there is no common factor of 2 and 5 other than 1. So we can make the claim that x times x plus 1 times y plus 1 is equal to 12. And now we do the same thing with the exponents of the 5s. And we can set up two equations with two variables. That means we can solve. So what we get are these equations. Now, instead of factoring out and solving something that is a mix of a cubic and a quadratic, what we're going to do is we're going to divide the first equation by the second. So when we divide, we get that x over y is equal to 2, so x is equal to 2y. This is a very important relation that we will plug into this orange equation here. The less substitution, the better. Now what we can do is we can just plug in values for y, and right off the bat we see that y equals 1 works. 1 times 2 times 3 is equal to 6. But as mentioned in the previous part of the video, I'm not a guess and check type of guy. And I don't want to factor out the cubic, so what I noticed, this is really clever, that y times y plus 1 times 2y plus 1, all over 6, is equal to the sum of the consecutive squares. This is 1 squared plus 2 squared plus 3 squared all the way plus y squared. And actually, I may be coming out with 2 proofs, maybe 3 of this fact, if, I come up with a third one in the near future. So, the sum of how many consecutive squares is equal to 1? Well, 1 consecutive square, obviously. So, yeah, y is obviously equal to 1 from there. And now, from the blue equation, we get that x is equal to 2. And now comes the grand finale. N is equal to 2 to the x times 5 to the y, which is equal to 2 to the 2 times 5 to the 1, which is equal to 4 times 5, which is 20. And that is the answer. Now we can do a quick check, just to make sure we didn't do anything wrong. 20 times 10 times 5 times 4 times 2 times 1, right? All of the divisors multiplied, is indeed equal to 8,000. So we are good there, and we have solved this PUMaC problem and learned quite a bit in the process too. We just derived these 2 very useful formulas that you should really commit to memory. So this formula for the product right here, the product is equal to the actual number times the number of divisors over 2, and the formula for the number of divisors. So that's 1 exponent plus 1 times another exponent plus 1 of all the primes. So those 2 are really important formulas, and we use them just now to guess and checklistly derive the answer to this problem. Challenge for you. I will be coming out with challenges at the end of each video from now on, probably, unless I don't come up with a challenge, which should be quite rare. Anyway, so this video's challenge. Try to find a formula that is similar to the formulas we derived in A and B, right here, that represents the sum of the divisors of n. Leave your answer in the comments, and I'll see you in the next video. Bye, and thanks for watching.